In today's lesson, we are mastering the relationship between graphs and equations, specifically focusing on the intersection of lines and curves. We will learn to determine intersection points using simultaneous equations, use the discriminant to analyze the nature of intersection, and solve exam-style problems involving tangents and secants. Understanding this is vital because it bridges algebra and geometry. In the Cambridge 9709 Pure Mathematics 1 examination, these concepts are frequently tested in coordinate geometry and functions questions, often requiring you to find unknown constants where a line is a tangent to a curve. When we talk about the intersection of two graphs, we are looking for the points where they meet. At these points, the x and y coordinates satisfy both equations simultaneously. To find them, we equate the expressions. If we have a curve and a line, we set f of x equal to mx plus c. The number of real solutions to this resulting equation tells us exactly how many times the graphs intersect. If there are no real solutions, the graphs never meet. Let's focus on the intersection of a line and a quadratic curve. This is a staple of the 9709 syllabus. First, consider the line y equals mx plus c and the quadratic curve y equals ax squared plus bx plus d. When we equate these, we get a x squared plus bx plus d equals mx plus c. By moving all terms to one side to set the equation to 0, we create a new quadratic equation in terms of x. Ax squared plus the quantity b minus m times x plus the quantity d minus c equals 0. The behavior of the line relative to the curve depends entirely on the discriminant of this new equation, which we denote as capital delta. Look at this visualization of a parabola and different lines. First, if the discriminant is greater than 0, there are two distinct real roots. The line is a secant, cutting through the curve at 2 points. Second, if the discriminant equals 0, there is exactly one real root. This means the line is a tangent. It just kisses the curve at a single point. Finally, if the discriminant is less than 0, there are no real roots. The line and the curve never meet. Let's apply this to a typical problem. Find the set of values of k for which the line y equals x plus k intersects the curve y equals x squared minus 3 times plus 2 at two distinct points. First, we equate the two equations to find where they meet. X squared minus 3 times plus 2 equals x plus k. Now, we rearrange everything to one side to get the standard form ax squared plus bx plus c equals 0. This gives us x squared minus 4 times plus the quantity 2 minus k equals 0. Here our coefficients are a equals 1, b equals negative 4, and c equals 2 minus k. Since the question specifies two distinct points, we must have a discriminant greater than 0. b squared minus 4ac is greater than 0. Substituting our values, the square of negative 4 minus 4 times 1 times the quantity 2 minus k is greater than 0. This simplifies to 16 minus 8 plus 4k is greater than 0, which is 8 plus 4k is greater than 0. Solving for k, 4k is greater than negative 8, so k is greater than negative 2. So for any value of k greater than negative 2, the line will intersect the curve twice. Let's look at a question typical of the Cambridge 9709 paper. The line y equals 2 times plus k is a tangent to the curve y equals x squared minus 4 times plus 12. Find the value of the constant k. To solve this, we start by equating the line and the curve. Now, we rearrange into the standard quadratic form. For this specific quadratic, our coefficients are a equals 1, b equals negative 6, and c equals 12 minus k. The key word in the question is tangent. This tells us that there is exactly one point of intersection, meaning the discriminant must be equal to 0. Substituting our values into the discriminant formula, negative 6 squared minus 4 times 1 times 12 minus k equals 0. 36 minus 48 plus 4k equals 0, which simplifies to negative 12 plus 4k equals 0. Solving for k, we find 4k equals 12, so k equals 3. In an exam, using the discriminant is much more efficient than trying to solve for x first. It directly links the geometric property of tangency to the algebraic condition of the discriminant. Let's look at where students often lose marks in these types of questions. First, a very common error is failing to rearrange the equation into the correct standard form. Notice that you must combine the line and the curve into a single quadratic before identifying your a, b, and c values. The discriminant only works on the relationship between the two, not on the curve alone. Second, students often forget to use brackets when substituting negative numbers into the discriminant. In the previous example, b was -6. If you write -6 squared without brackets, your calculator or your brain might give you -36. However, any real number squared is positive. This sign error will completely ruin your final value for k. Third, misinterpreting the inequality for distinct points. The phrase two distinct points strictly requires the discriminant to be greater than 0. If you use greater than or equal to, you are including the case where the line is a tangent, which is incorrect for this specific wording. In the Pure Mathematics 1 exam, the way you structure your working is just as important as the final answer. Examiners look for specific method marks. First, always show the substitution into the discriminant clearly. Even if you make a calculation error later, showing b squared minus 4ac with your values inserted secures you the method mark. Second, be precise with your terminology. If the question mentions a tangent, explicitly write down for tangent, discriminant equals 0. This shows the examiner you understand the underlying mathematical reasoning. Third, look out for the phrase set of values. This is a huge hint that your answer should be an inequality, such as k is greater than something, rather than a single number. If the question asks for the value, expect a single constant. Finally, manage your time. If you find yourself doing complex long division or using the quadratic formula to find x when you only need to find a constant k, you are likely taking the long route. The discriminant is your fastest tool for intersection nature problems. It is time to test your understanding. Please pause the video and attempt these 3 questions. Easy. Find the points of intersection of the line y equals 2x plus 1 and the curve y equals x squared minus 2. Medium. The line y equals kx minus 5 is a tangent to the curve y equals x squared minus 4x minus 1. Find the 2 possible values of k. Hard. Find the set of values of m for which the line y equals mx plus 2 does not meet the curve y equals x squared plus 3x plus 6. Take your time with the algebra, and remember to use the discriminant for the medium and hard problems. Let's go through the easy question first. We equate them. X squared minus 2 equals 2x plus 1. Rearranging gives x squared minus 2x minus 3 equals 0. Factoring the quadratic, x minus 3 times x plus 1 equals 0. So x equals 3 or x equals -1. To find the y-coordinates, substitute back into the line equation. If x equals 3, y equals 2 times 3 plus 1, which is 7. If x equals -1, y equals 2 times -1 plus 1, which is -1. The intersection points are 3, 7, and -1, -1. Now for the medium question. We set the equations equal and rearrange to get x squared minus, open bracket, 4 plus k, close bracket, x plus 4 equals 0. For a tangent, the discriminant delta equals 0. -4 plus k squared minus 4 times 1 times 4 equals 0. Simplifying, 4 plus k squared minus 16 equals 0. So 4 plus k squared equals 16. Taking the square root, 4 plus k equals 4, or 4 plus k equals -4. So k equals 0 or k equals -8. Finally, the hard question. We equate the expressions and rearrange to x squared plus, open bracket, 3 minus m, close bracket, x plus 4 equals 0. For no intersection, the discriminant delta must be less than 0. 3 minus m squared minus 4 times 1 times 4 is less than 0. This simplifies to 3 minus m squared is less than 16. This inequality means negative 4 is less than 3 minus m, which is less than 4. Subtracting 3, we get negative 7 is less than negative m, which is less than 1. Multiplying by negative 1 and reversing the inequalities, we find m is between negative 1 and 7. To summarize our lesson on the relationship between graphs and equations. First, to find intersection points, always begin by equating the expressions for y to form a single quadratic equation in x. Second, the discriminant, b squared minus 4ac, is the definitive tool for determining the nature of intersection. Remember, d greater than 0 means 2 points, d equals 0 means a tangent, and d less than 0 means no intersection. Third, in the Cambridge 9709 exam, look for keywords like tangent, distinct points, or does not meet to decide which discriminant condition to apply. Fourth, always simplify your combined equation into standard form before identifying your a, b, and c values to avoid common sign and coefficient errors. Finally, keep your working clear and show every substitution step to maximize your marks on the paper.